We are now going to show the back cab rule. I was inspired by an email sent by one of the students, and I stayed up. I got up at 4 in the morning to do this one morning, and I've got a script ready, so hopefully we can get through it okay. I want to start right away by looking at the result we used in Maxwell's equations, and this is the back cab rule, and we just used this back cab rule using pattern matching to do this. Now, what you'll notice when you use the back cab rule is you're wondering about this term here. In fact, you can write this whole thing in the back cab in 16 different ways. Why is that? Because you can put this vector in front or behind the scalar. The same here, that's 2 ways, and then flip these around in 2 ways and this around in 2 ways. 2 times 2 times 2 times 2, 16 different ways. Now, only one of those really corresponds to what we have here, because whereas you can put the b in front or behind, when you have these gradient operators, they're working from left to right. So working from the left is not the same as flipping it around. In any case, you can show this directly now, and we want to see where this comes from. So that's the first question. Now, there is one tendency, and that is, let's do brute force. So I'll just indicate brute force. Now, let's see what happens if you try to brute force this. So the brute force. And we'll see what the problems are if you try to just grind this thing out. So if you try to grind it out, A is going to have 3 components. Similarly, B. And similarly, C. Now, let's see what happens and how messy it gets real fast. So what does B cross C look like? Well, first of all, if you set up the determinant ijk, and we put in the b's here, like you learned in your math classes, you can see that typical terms are going to look like, for example, the I component bycz, and there's an I hat here, or I, not I is just the unit vector, minus bz cy. So every term has got 2 contributions from these minors, and there are 2 numbers here. If we then take this result and put it in with A, we'll have A's here, and the result, the B cross C's here, and you can quickly see that instead of the 6 terms, 3 times 2, that you get when you do this, you're going to end up getting 12 terms, and they're going to have AX and CY and BZ all multiplied together. So you can do this, but it is a glorious mess. And the 2 disadvantages are, first of all, 1, no intuition. 2, algebraic errors, real easy. 3, you need symbolic algebra like Wolfram. And when you get the Wolfram result, you'll get all those 12 terms done perfectly, but you have to group them to see where you get these dot products and stuff. so that's not very attractive. And I'm not going to put a big X through this. So what's another way to approach this problem? The other way to approach this problem is to look at the result. We start with two vectors B and C, and we end up with a linear combination of B and C. Oh, so why is that? Well, let's say B is this yellow drawing and B is this orange. So there's B and C. Now they could be off somewhere like this, but we can rotate and choose our axes, so we notice that B and C lie in the same plane. Now, when we take the cross product, it lies along the pink drawing utensil. It's clear that for an arbitrary A, it's kind of hard to hold all these. Here's A. So A is sticking out at an angle like that. It has all three components. B and C define a plane. Two vectors define a plane. And the pink cross product, if we have a unit vector, defines the normal. So that is the equation of a plane. Then when we cross these together, we end up back in the BC plane, in this plane. So we're going to use that. Why don't we use it? And there's a little trick to using it. So let's see what the trick is. The trick is not really much of a trick, but let's look at the BC plane first. So the BC plane. So here is the BC plane, and I'm going to take what we would call the x-axis is along the vector B. And I'm going to take what we'd call the y-axis. I'm going to call it not y, but I'm going to call it the t-axis. Now, along each of those axes, there are unit vectors. So here's one. That's the B unit vector. And here's the t unit vector, t hat. Now, I just said that when you're in the BC plane, you get a normal vector, which is in the direction of the cross product. So we can define a third unit vector n, and that unit vector n is going to be, and I've got the different color, B cross C divided by the magnitude of B cross C. So we have a new coordinate system. I'll draw it here. It's going to be this. This is with the B hat direction. This is in the T hat direction. And this is in the N hat direction. That is an orthogonal coordinate system. Now, the next thing to do is to write down the cross product relationships for these unit vectors. So in order to do that, I'm going to do what we learned in the math course. I'd write this as B, T, N. B, T, N, and these refer to the unit vectors. So B is like our usual x-axis, T is y-axis, and N is z-axis. So this would be like I, J, and K. And so we know that I cross J is K. So B hat cross T hat equals N hat. Then you go to T. T hat cross N hat is equal to B hat. And finally, N hat cross B hat equals T hat. So we'll need these three cross product relations. It's like I, J, K. I cross J is K, J cross K is I, and K cross I is J. So we know that from our work in cross products. Now all we have to do is write down the three vectors A, B, and C in terms of these unit vectors. and see what happens. Now, let's do that. So B is real easy. I'll change the color. I'll go back to orange. So B is real easy. We'll call it magnitude of B times B hat. C, well, what's C? I'm going to label the components of C as, you can see that the C vector sits in the B hat, T hat plane, so it's a linear combination of that. So I'll write it like this: CB B hat plus CT T hat. And what about A? Well, A has all three components. So it's going to have component along B hat plus a component along T hat plus a component along N hat. So I think now all we have to do is use these three relations, and here are our vectors, and grind everything out. So that's what I'm going to do. I'm going to grind everything out, and while you're watching, you can think about playing with those three cross product terms that I just have here. Make sure that I didn't drop a minus sign or something like that. Now, this technique for solving the problem, I can't take credit. I read about it in a book by a very famous mathematician many years ago. His name is Fritz John, and he wrote a book with his colleague Richard Courant, Courant and John, volumes 1 and 2, and this is how he solved the problem. And I think this is a really nice way to do it and gives you an intuition about solving these kinds of geometrical problems. So let's see what we can do. The rest is really easy. You can start working out already while I'm erasing. So look at the first cross product. B only has one component. So that first cross product is super easy to do. And then the next one will have two terms. So instead of 12 terms, we're going to have, I think, 2 terms. And then we just have some interpretation to do. So we've done the hard work already. We have very little algebra to do. We've got an intuition of the geometrical setting. And we're pretty much done. It's just a bit boring, but I want to go through it anyway for you. And let's see, hope you're doing okay. This is all fine. I made no minus sign errors, and let's continue the story. All right, so we have everything set up. I've got papers here so I don't make a typo. So let's do B cross C. Well, B only has the B hat component, and C has a B hat and a T hat. So we cross product. B hat cross B hat is 0. B hat cross T hat is N hat. Wow, one term. Instead of 6 terms, we have 1 term. So our answer there is this. And B hat cross T hat, I just said, is N hat. Great. Now we're going to do A crossed with that. So A crossed with B cross C. So we're getting there. A cross B cross C equals. I'll talk you through it. B cross C only has an N hat component. So that means that when I cross it here, this cross term with A will disappear, and you'll be left with these 2. So we'll have 2 terms instead of 12. Pretty good, huh? So if you write this out, So I'm going to write it all out. AB B hat plus AT T hat plus AN N hat. So there's A crossed with this. Hope I get it in here. B C T N hat. Great. Now, we're going to have a B hat crossed with an N hat, and we're going to have T hat crossed with N hat and N hat crossed with N hat. So B hat crossed with N hat. So B hat crossed, that looks like minus T hat. So we get minus T hat times the numbers. So it's AB, BN, so it's AB, this thing here. So that's going to be AB times magnitude of B times CT. And now T hat crossed with N hat is B hat. So we have a B hat, and the numbers are AT, CT, magnitude of B, B hat. Oh, look at this term here, ATCT. This term is B. So you think, oh, is this A dot C in front? Not quite. What we have to do is deal with this T hat term, negative T hat term. So to do that, I'll put it down here. We know that C equals CB hat plus CT T hat. So if we solve for CT T hat with the minus sign, what do we get? We get, just rearranging this with the minus, minus CT T hat is equal to CB hat minus capital C. So what we do is we take this expression and replace the minus CT T hat with this right-hand side. So let's do that. Minus CT T hat is this piece. So let's put that in. That's CB hat minus capital C. So that takes care of that, times AB magnitude of B. And this is still there. Okay, it's now just a straight algebra thing. So what do we see here? Well, we've got a CB B hat with AB times this. So let's combine those terms. And so we're going to have, this is equal to just a sec, CBA, AB, so this, I'm going to write this out slowly, minus C times, so I'm going to take this term here, that's minus C times AB, CB, A dot B, CB, yeah, A, that's right, minus C, AB, CB, something wrong here. We did the CT, so we have AB times C. Just a second. I knew this is the tricky part. Every time I get this wrong. So we have minus C times A minus C AB times magnitude of B. That's this term here. Now we do this term. This term is CB B hat AB times this plus this term. All right, so what is this? What is this? AB, oh, this should be magnitude. So minus C, the B component of A times the magnitude of B. Well, what is this? This is, look at this, A dot B. A dot B is, you multiply the components, which is magnitude B, AB. So this first term is equal to minus C A dot B. How about the second term? We factor out this, and we have AB CB plus AT CT. What's that? Take the dot product of C and A. CB, AB, CT, AT. That's exactly what we have here. So this is just A dot C, and this, of course, is B. So this is equal to B into A dot C. There's the back. There's the cab. Hooray, we're done. We did it, and we now know where this comes from, and we have the geometric intuition, and hallelujah.